Hey, I'm Anirudh, and good morning, good afternoon, good evening to everyone. In this session, my colleague Andy and I are going to be talking about AI and machine learning technology enabled patient finding solutions. With the changing therapeutic and clinical landscape, where we are seeing increased domination of targeted therapies aimed at niche patient populations, it's becoming difficult for biopharmaceutical companies to improve patient outcomes. This is partially because finding such niche patient populations and finding them on time and for the right product is very challenging. Further, once patients are on therapy, and given the limited size of the patient population, it becomes even more important to improve adherence and identify patients at risk of non-adherence. Given these trends and challenges, companies are increasingly looking to innovative and precise solutions to find patients. And with the advances being made in technology and increasing volumes of data, AI and machine learning is emerging as a strong capability in meeting the need to find patients. AI/ML patient finding can be applied across the patient journey, though there are four main applications. That is to find patients at risk of developing a condition, finding undiagnosed patients, finding patients at the risk of developing non-adherence, and finding patients who are not being treated appropriately. And with these solutions, biopharmaceutical companies can improve outcomes in terms of disease prevention, treating patients before complications arise, disease control, and initiation of the right line of treatment. To briefly talk about the process of applying AI/ML to find patients. So we start the process by creating the right set of cohorts to the problem at hand. Let's use disease detection as an example. Typically, we create two cohorts, positive or a case cohort composed of diagnosed patients, and a control cohort composed of those patients not having the disease. Through these cohorts, we create two data sets, one for learning and another one for validation. Once this is done, the AI/ML model goes through the medical history of these patients and identifies key data-driven and clinical features. And based upon these features, the model learns the unique patterns in the patient's medical history. And this is followed by applying the model on an unused data set to validate its performance. That is how well the model can predict patients who have a disease. Once we are satisfied with the results and the precision, the model is then applied to a broader set of patients to find the larger undiagnosed patient pool. Also, depending upon the need, we further enhance the solution by mapping these patients to their treating physicians or overlaying patient and physician subnationally. But herein lies a major challenge. AI modeling is time consuming, data preparation is messy, and creating the right cohort is complex. And further, making AI/ML interpretable to all is quite difficult. To move from doing one-off predictive model to truly scaling AI/ML solutions across different therapy areas and geographies, it needs to have a strong technology enablement. At IQVIA, we are well aware of these challenges and therefore have invested in developing AI-powered technology solution to enable true scale. There are three layers to the technology. The first that you're seeing on the left-hand side is the data layer composed of IQVIA real-world data on a big data factory, where the data sets can be combined with client and other third-party data sets. And in the middle, there is the analytics layer, which automates a lot of aspects. And an important part of this technology is the AutoML engine, which helps to identify and deploy the right model in a fraction of time it would have taken if you would do so manually. The final layer is the interactive interface in form of web apps to enable end users to derive actionable insights. IQVIA's AI/ML powered technology is a modular ecosystem with each component created to address the challenges in scaling AI/ML. For example, there is explainable AI module, part of our glass box approach to provide our clients and their data scientists with full transparency on model performance, key features that are just not at a global level, but at a subpopulation level. Another example is the cohort creation module that can create complex and tightly defined cohorts to train the models. Now, I had talked about the advantage of using technology to scale up, not just to different therapy areas, but across geographies. We are actively expanding the technology's capability to find to different geos. And for each geo, we need to adapt the solution and the process based upon the data sets that are available, the granularity of the data, and the legal constraints. To give an example, in case of Spain, we cannot deploy the solution at a subnational level. Whereas in case of US, we can get very granular. I'll briefly show you how the process differs by geography. First, with the example of Germany. Now in Germany, we typically train the model on EMR data and apply it on LRX data. The reason is EMR data has diagnosis information, whereas it has limited coverage. On the other hand, LRX data has got a wide coverage, but has no diagnosis information. Once the model has been applied and we have identified focused patients, we further enhance the analysis by building a longitudinal view of the patient treatment patterns, applying custom rules, and building their profiles. In parallel, we also develop models to identify physicians of interest. The use case may be different, for example, to identify those physicians who can drive referrals versus those who can drive diagnosis or initiation of a treatment. We then overlay the patient and physician insights at a subnational level to unravel unmet opportunities. And finally, all of these elements come together on an interactive dynamic. Now, another example, in this case, the US. In the US, the methodology has got two key differences. Firstly, and typically, we do not rely on different data sets to solve the issue of diagnosis and coverage. IQVIA US claims data has got a very high coverage and has diagnosis information as well. The second aspect that I'm highlighting here is where the process differs, is in fact that in case of US, patients can be mapped to physicians directly, and thereby expanding the richness of insights. The rest of the processes remain more or less the same. I'm going to take you through a couple of examples of how IQVIA's AI/ML-powered technology is providing scale and efficiency-driven patient-finding solutions. We've enabled the solution in Germany, wherein one of our clients wanted to launch a brand for uncontrolled asthma. And as you would be aware, there's a considerable overlap of treatment for asthma and COPD. With the use of technology and AI/ML, we firstly were able to identify true asthma patients with a high level of precision of 86% as compared to rules-based methods, and thereby eliminating 30% of non-target patients. We further identified patients with uncontrolled asthma and enable insights and profiling of these patients at subnational level to benefit of our client to identify focus areas of unmet needs. Our client was able to better understand the unmet need and was able to offer its treatment to the right set of patients, thereby improving outcomes of these patients. As a matter of fact, in a 6 months analysis of these patients on new treatment, we saw a 17% reduction of uncontrolled status. Further, we were able to deliver the solution 2.5 times faster than before and pass on a 20% saving due to higher efficiency. Another example, and this time it's for a rare disease franchise in the US. Our client wanted to move away from business rules-based alerts to machine learning predicted alerts for 5 brands across 4 different rare indications. Using AI/ML-powered technology solution, we built alerts to identify patients likely to be diagnosed with the rare indications, and we enabled further insights for the client's teams through interactive dynamic interface. Further, the AI/ML models led to an improvement in prediction, in which, as part of a historical comparison, level patients predicted by the model were diagnosed with a condition as opposed to 0 by rules-based methodology. For an ultra-rare disease, ultra-rare condition that is, this is a significant boost. Now I'll be asking my colleague, Andy, to provide a quick demo of the platform, following which I'll summarize the key takeaways.
Thanks, Anirudh. So I'm going to show you here the user interface level of the platform, which brings together the automated patient finding algorithms, the use of integrated real-world data, and the machine learning methodologies which Anirudh referred to in the presentation. All of this is pulled together in a single purpose-built application to facilitate advanced and fast access to insights. The application I'm going to be focusing on today is the Patient Population App for Germany. And I'll be demonstrating the asthma market with specific focus on pinpointing moderate to severe asthma patients with unmet needs. This is a scalable global capability that is adaptable for each therapeutic area or market. The Patient Population App consists of a number of modules which allow us to quantify and characterize patients and to provide a longitudinal view of treatment line progression and associated switching factors. So drawing our attention to the Patient Population tab, which is utilizing electronic medical records and pharmacy claims data with all the elements of advanced machine learning, which automatically finds and presents these patients of interest. So here we see this total patients. This quantifies and characterizes 2.24 million moderate to severe asthma patients, which have further been segmented into patients with unmet needs. In here, uncontrolled patients are being represented as those with exacerbation and in need of reliever treatments, such as OCS or SABA. As well as this, we can identify patient severity levels as shown here to help prioritize patients' reach. This user interface, which is configurable by disease area, is interactive to allow us to drill down into sub-cohorts of patients on multiple dimensions. For example, we can segment patients based on their dominant therapy, which is a proxy for their level of severity. We see here the prominent co-medications, also the treatments in the broader respiratory market, as well as providing an understanding of patient demographics such as age and gender. In the map here, we can also see the subnational distribution, which Anirudh referred to earlier, and with the ability here to also toggle to identify areas of high disease prevalence. So now I'm going to show you a quick illustration of how we might want to identify hotspots of adult patients with unmet needs. So here, I'm simply going to select the uncontrolled option in the patient segment filter and narrow down my patient age group to exclude anyone with an age of less than, say, 20. So we very quickly see here that Bergisch Land has the highest prevalence worthy of focus. We then know, by selecting it, that we could prioritize the 6,700 patients roughly, and prioritize them based on patient reach, based on severity or burden of the disease. Let's now dive into the patient treatment journey with a view to identifying key switching factors associated to patients with escalating and de-escalating treatment. I'll be comparing patients who have been on ICS/LABA and have either transitioned to a triple therapy or monotherapy, being ICS. My first cohort represent patients who have transitioned to triple therapy, and it's evident that more than 50% of these patients are being seen by pulmonologists and are categorized with uncontrolled asthma. Also, we see that 31% of the patients are on SABA medication versus 17% on OCS. Furthermore, we have a clear view on their geographical distribution and age gender. If I was to compare this to patients on ICS/LABA who have had de-escalating therapy, what we see is a prominent increase in the number of controlled asthma patients who are seen by general practitioners. Also, a prominent skew towards SABA treatment versus OCS, which is typically prescribed by specialists. This has provided us with an evidence-based treatment journey dynamic that allowed us to quickly compare prevalence of factors associated to transitioning treatment. These were some example scenarios that enabled us to understand patients with unmet needs. So to summarize, the Patient Population app provides this holistic view of the eligible patient population and treatment journey, underpinned by our advanced machine learning capability and real-world data. The platform is now servicing clients globally to deliver improved precision for patient finding, interactive granularity across multiple metrics, and an improvement in patient outcomes across disease areas. I'm now going to hand over to Anirudh to conclude the presentation.
Thanks, Andy. So to summarize, clinical and therapeutic trends are driving an increased need to find patients to improve outcomes. Application of AI/ML can help both, that is finding patients and improving outcomes. Applications span across the patient journey. But to truly scale AI/ML patient finding, strong technology enablement is needed. Application of technology helps in bringing in efficiency, standardizes tasks and processes, and helps in end user adoption of outputs. Thank you. Please reach out to us in case you have any questions. Moving on to Q&A.